So question 5.1 is based on an old exam paper. The first part and the second part are relatively straightforward, and the third part is perhaps a bit more challenging, and certainly people struggled a bit more with it. So I'll go through that bit. I'll try and go through that bit more slowly than the first two sections. So it's a bar. Let's say that's our bar, and it gives us the velocities at point A and point B. So it's like the bar is going like that, essentially. So let me draw around this. And that's our point A, and that's our point B. And it tells us that this velocity is 20 centimeters per second, and this velocity down here is at an angle to the horizontal of 45 degrees. And part 1 asks calculate the angular velocity of the bar, and then the velocity magnitude at B, and then the velocity magnitude at the bar's centre of mass, which is halfway along. But we'll get to that. So that's the centre of mass. So the first step, well, there are a number of ways to do this. We could, if we go to our lecture slide, we could implement an expression for the velocity of B equals the velocity of A plus the velocity of B relative to A. But we're going to do that graphically in a simpler way by finding out where the instantaneous centre is. And the instantaneous centre is if we draw lines that are perpendicular to the velocity vectors on the rigid body. So this is a perpendicular line here, down here, and then a line that is perpendicular to the velocity at point B. So I did this freehand, so this is not quite 45 degrees. Doesn't look 45 degrees at all, does it? This then, the point where these two lines intersect, is the instantaneous centre. And actually I think we covered that at the end of lecture 4. So we can use that now because this velocity here, the velocity of A, is actually the tangential velocity of a fixed axis rotation around the instantaneous centre. This length here is 0.5, and because this is 45 degrees, it's not a great sketch, but this will also be 45 and that will also be 45. So that means that this length here is also 0.05 meters, because it's given us that the length of the bar is 5 centimeters in the question. So because this velocity is the tangential velocity of this fixed axis rotation, we can use the fact that, let's do it here, the tangential velocity is equal to omega times r. And r in this case, this is, let's say it's RA, it's the length of the line between the instantaneous centre and point A. So that is omega times by 0.05. And the tangential velocity magnitude is 0.2. So with a bit of rearrangement, we find that the angular velocity of the bar is 0.2 divided by 0.05, 4 radians per second. That's the first. Give it a nice box to make it easy for the marker. So that's the first part of the first part. Now it's asking for the velocity magnitude at point B, and because it's a fixed axis rotation around this instantaneous centre, we're looking for the tangential velocity of point B. So really I should put a subscript A here. And that, well, it has the same angular velocity but a different r. So it'll be omega times rb. And rb, if this is 0.05 and this is 0.05, then this is pretty simple. It should be equal, so rb is equal to the square root of 0.05 squared plus 0.05 squared. That's rb. It's using Pythagoras. So rb is equal to square root 0.05 squared plus 0.05 squared. That's 0.0707. So 4 times 0.707. I was right, 0.0707. So answer times 4 gives you a velocity magnitude of 0.283 meters per second, which is, yeah, that equals there. So that's the second part of the first part of the question. So the third part asks for the velocity magnitude at the centre of mass, and that's really simple because all we need to do is, it's the same angular velocity again, but we've just got a different value for r. So this length between the instantaneous centre and the centre of mass, RCM, is equal to, again using Pythagoras, this length is the same, but this length is half the length because it's this is where the centre of mass resides, halfway along. 0.025 squared. So that's equal to 0.05 squared plus 0.0. Is that right? Yes, 0.0559. So once we put that now into our standard expression, so omega times RCM, it's that times 4, because that's the angular velocity. So that's the final part of this part 1. That's 0.224 meters per second. Okay, so all we're going to have to remember from this, well, I might bring back that diagram later. Moving on to the second part now. I'm going to draw another little sketch. So we've got point A here to point B. This is a length 0.05, just to remind us. And part 2 asks us to calculate the centripetal acceleration of point B relative to point A. Now, this acceleration of point B relative to A might be, for example, like in this direction. But it's got 2 components, a tangential component, and the length of that is denoted by that expression. So the acceleration of B relative to A in the tangential direction, and the mods here tell you that this is the magnitude of that And then you've also got a centripetal acceleration, and that is the acceleration of B relative to A in the radial direction. So that's B backslash A in the radial direction. And if you go to the notes, it tells us what the magnitudes of the radial component and the tangential component are in the two cases. So for this question, where it explicitly asks us for the centripetal component of the acceleration of B relative to R, we want the top expression. So the acceleration of B relative to A in the radial direction, so the centripetal component, is equal to RAB, so this length, multiplied by omega squared. Now omega we calculated in the first part of the question, which was 4 radians per second. So that equals 0.05 times 4 squared, which gives us 4 squared plus, times 0.05, 0.8 meters per second squared. So that's part 2. Now part 3, now this is the trickier part. And in the text solutions, it's maybe more complicated than it needs to be. So I'm going to try and solve this graphically, and hopefully it will make a bit of sense. So it says in the question, given that the angular acceleration of the bar is 40 radians per second squared clockwise, so it now tells us that there is an angular acceleration clockwise. And that is 40 radians per second squared. And that the translational acceleration of point A is 5 meters per second squared upwards. So there's a velocity of A here. This is the velocity of A. And its magnitude, the acceleration of A, Acceleration of A, the magnitude of the acceleration of A is equal to 5, and it's upwards. So given those two things, we've got this angular acceleration and we've also got this linear acceleration of A. What is the total acceleration at B? So it asks you the magnitude and the direction. So there are a number of things for us to calculate, but first of all, it's worth calculating what the tangential component of the acceleration of B relative to A is, because we are going to eventually use, this expression here. So let's write that down now. Acceleration of B plus the acceleration of A, acceleration of B equals acceleration of A plus the acceleration of B relative to A. So we're going to need all the components of the acceleration of B relative to A in order to evaluate this equation. So that component, and it tells us what it is down here, it's equal to the length RAB multiplied by the angular acceleration. And the angular acceleration is given here as 40. So that is going to equal 0.05 times 40, 2. So we have 2 meters per second squared. So we can do this symbolically, but I'm going to solve this equation graphically because this is the way we've done it in the lectures, and I think it's simpler. So we want to find out the acceleration of B here. And we don't know where this is and what direction this is going to be, but we know that it's composed of two vectors. the acceleration of A, which is directly up, plus the acceleration of B relative to A, which itself has two components, so it's got this component and this component. So in total there are three components that are going to be added together to give you the acceleration of B. So ignore this, which is a drawing of the acceleration of B relative to A. We've got these two components added to this component will give you the acceleration of B. So we can do that graphically because these are perpendicular to each other. So we're going to start here, let's start down here, and we're going to start by adding acceleration of A to our origin, and it's going to take us all the way up the top here to a distance of 5 meters per second squared from the origin. Now we can actually add this component of the acceleration of B relative to A, and it's going to just take us back in the opposite direction. And this length here is 2. So what we're left with here is a length 3. So we've gone up and now we've come back down again. But we've got to add this final component here, which is the acceleration of B relative to A in the radial direction, which has a magnitude of 0.8. So I'm not really drawing this to scale, but it doesn't matter. Let's just assume that that's 0.8. It looks a lot longer than 2, but there we go. So that's 0.8. So that means we've gone up, that's that vector, then we've gone down and across, which is this vector. So that there is the acceleration of B. That's what we're trying to find out. And in reality, it's actually a lot more. It's going to be in that direction because I've not drawn 0.8 to scale. So what is the magnitude, first of all, of that? We'll use Pythagoras with 3 and 0.8 plus 0.8 squared. Root of 3 squared plus 8 squared is equal to 3.1 meters per second squared. That's the magnitude. And it also asks what the direction is, and we're going to give the direction as an angle from the horizontal, so positive x direction. So what is this, first of all, this internal angle here, theta? Well, the tangent of that angle is equal to the opposite over the adjacent. So theta is going to equal the arctangent of 0.8 over 3. So that's what theta equals. So arctangent 0.8 over 3. Okay, we want that in degrees. So 180 divided by pi. So that's 14.9 degrees. So if we're looking at anti-clockwise from the positive x direction, we need to add 90 degrees to that. Answer plus 90. So it's 105 degrees. So that's anti-clockwise from positive x. And yeah, well, I've already drawn it in orange. That's the answer.